Welcome back to Honors Calculus. In this video, we're going to look at some substitution tricks. Specifically, there are two tasks that I want to look at that will allow us to extend the idea of a U substitution that we saw in a previous video. The first one is a little bit more general, but honestly fails as often as it succeeds. As we saw in that previous video, very often an expression cannot be integrated analytically. The second one is going to take this idea of substitution and look specifically at how it interacts with definite integrals. So without further ado, let me get my head out of the way and let's dive into the first example. All right, I'd like to look at the integral x dx over the square root of 2x plus 5. And we see here that we've got some mess going on. Right? We've got a square root in the denominator of the fraction, and we've got something that's not just x inside the square root. So my natural inclination, whenever I see something like that, is to see if a substitution will work. Let u equal 2x plus 5. Well, by going through that, that would give us that du is simply 2 dx. And that looks promising, I guess is the word, but not quite. Because I've got an x up here and nothing related to it down below, right? I need 2 dx and I have x dx. And so I'm going to try to rewrite this equation, u equals 2x plus 5. If I solve for x, subtract 5, then divide by 2, I get that x is u minus 5 all over 2. And let's try substituting that in. All right, I need to get a 2 in here, so I'll put a 1/2 in front. And so I'm going to be left with that 1/2. The x turns into u minus 5 over 2. The dx turns into du, well, the dx with the 2 that we introduced. And then in the denominator, I have square root of u. Right, rearranging this a little bit. Getting that 2 outside of the integral, right? Constants are always annoying. So let's call that 1/4 the integral of u minus 5 over the square root of u. And then let's split that fraction up. Right? U divided by the square root of u is the square root of u. And then we have 5 over the square root of u. And each of those on its own is something we can, in fact, work with. All right. The integral of u to the 1/2. Well, 1/2 plus 1 is 3/2, so we'll have 1 over 3/2 times u to the 3/2. The integral of u to the negative 1/2. Negative 1/2 plus 1 is positive 1/2. So we will have 1 over 1/2 times u to the 1/2 power. And then, of course, because it's an indefinite integral, we always have plus our arbitrary constant of integration. Cleaning up a little bit, 1 over 3/2 is 2/3. 1 over 1/2 is 2. And so we'll end up with 1/6 u to the 3 halves, and it looks like 5 halves u to the 1 half. And then finally, if I scroll back up and remind myself, u itself was 2x plus 5. And so we can finish off by making that substitution. Depending on what we're trying to do from here, it might be worth factoring out a 2x plus 5 to the 1 half. It might be worth rewriting this as a single fraction. It might be worth just leaving it alone. We don't have the context, so as soon as we have something that works, we'll end there and not worry about it any further. To show you when this sometimes doesn't work, I want to remind you of a problem from the previous video that we saw that we could not solve. Integral of sine of 2x squared. We looked at let u equal 2x squared, which would give us a du of 4x dx. And since there's no x out here anywhere, there's not really a lot we could do with that. I tried to show you that if we tried to introduce that by putting in a 1 over 4x times the sine of 2x squared times 4x dx, well, that gives me my 4x dx, that gives me my u here, and I guess we could try and see if something will work with this x. It's never a bad idea to try, but in this case, if we try to do that, it looks like if I solve for x here, I would get the positive or negative square root of u over 2. So that means that 1 over 4x would be, well, multiply that times 4, which I guess is the same thing as square root of 16, and we'll get 1 over the square root of 8u. And so after our substitution, we would have integral of 1 over the square root of 8u times the sine of u du. And that's no better than what we had before. Again, for those of you moving onward, we will be developing some techniques later on in the course. It turns out that this could be solved using a method called integration by parts, but that's beyond the scope of this video and of this course. That's something we talk about in the second semester of calculus. So if you're continuing onward, you might see it there. But for the tools we haven't made this thing any better. We haven't helped ourselves any. And that's what I mean when I say that this method sometimes is successful and sometimes is not. It is still a tool to put in your bag of tools, so it's worth seeing. Sometimes it works, sometimes it doesn't really help. But something is better than nothing. All right, let's take a look at the other problem that I told you we would look at today, where instead of an indefinite integral, let's take a look at the definite integral. How about the integral from 3 to 7 of the square root of 2x minus 1 dx? This is a definite integral, which changes things just a little bit. An idea that I'm going to emphasize here that we don't see all that often in this course, but for those of you who continue onward to multivariable calculus, Calc 3, you'll start to see some of these things show up there. We're going to be doing a change of variables. So in order to help us keep track of what's happening, instead of just calling my limits of integration 3 and 7, I'm going to call them x equals 3 and x equals 7. That way, when we change our variable in a little bit, we'll remember what's happening. But I am going to try a u substitution. This one is a fairly straightforward option. Let's let u equal 2x minus 1, which means that du is 2 dx. So we need a 2, which means we also need a 1/2. But with a definite integral, we have those limits to deal with as well. You have two options here. I do want to mention that some resources will tell you to just continue on with the integration and remember to substitute back in, replacing u with x, and then go from there. I personally find that it's worth taking the time now to simplify the limits of integration, take that step out early, and then you don't have to worry about it later. So what I'm going to do is I'm going to evaluate u at these two limits. So u of 3 is 2 times 3 minus 1, which is 5. And u of 7 is 2 times 7 minus 1, which is 13. And so with that, I can rewrite this as 1/2 the integral u goes from 5 to 13 of the square root of u du. And the value here is that once I remember that the integral of square root is 2/3 u to the 3/2, I just have to evaluate that at 5 and at 13. All right, 1/2 times 2/3 is 1/3. So we're going to get 1/3 times, well, 13 to the 3/2 minus 5 to the 3/2. I don't know what the square root of 13 or the square root of 5 is. We could rewrite that as 1/3 times 13 square root of 13 minus 5 square root of 5 if you are a fan of radical notation instead of fractional exponents. Is that better or is that worse? I don't know. It depends on the particular problem you're looking at. But the real idea here is that by changing the limits of integration when we perform our substitution, we don't have to worry about going back and substituting in the meaning of x when we perform a definite integral. You do have the choice. You can choose to leave all of your limits in terms of x and remember to substitute back in before you continue onward. I like mentioning that because if you're looking at textbook resources or other videos on YouTube, you're going to find that method used. There's about a 50-50 split among mathematicians over which of the two methods is more convenient. I happen to fall on this side of the argument, so I wanted to show you that, but I do want to mention the other option exists as well. All right, to wrap this video up, let's look at one like this for you to try. The integral from 0 to 1 of x times 1 plus x squared, the whole thing cubed, dx. All right, take a few minutes, see what you can do with that problem, and I'll see you in the next video.